Hello everyone. In this session, we can study one of the important parameters of a radioactive substance called half-life period, denoted by T half. So as its name indicates, T half or half-life period of a radioactive substance is the time required for one half of the radioactive substance to disintegrate. And the half-life period, its order can be of seconds, minutes, hours, days, months, and even up to many years. And the half-life period of a radioactive substance is unique. Each radioactive element will be characterized by its own half-life period T half. So let us consider a radioactive sample and let N0 be the number of atoms present in the sample initially, that is, we can take the time as 0. And the radioactive sample, as you know, it consists of a large number of atoms, that is, millions of billions of atoms of the order of Avogadro number of atoms. So after the end of one half-life, that is after the time T half, what happens to the sample? The number of atoms in the sample will be reduced to half. So after T half, the number of atoms will be N0 by 2. And again, after another T half, what happens? The number of atoms again reduces to half. That is N0 by 2 now becomes N0 by 4. And by the end of 3 T halves, what happens? N0 by 4 now becomes N0 by 8. And again, after one more T half, it becomes N0 by 16. That is, at the end of one half-life, number of atoms present in the sample will be reduced to 50%, or its mass will be reduced to 50%. And by the end of 2 T halves, the number of atoms or mass of the sample will be reduced to 25%, and then it reduced to 12.5% and etc. Now we can represent this process graphically. That is, we are taking a plot of number of atoms in the sample versus time. So initially at time t is equal to 0, number of atoms present in the sample is N0. And we can mark half of this in here, this portion, that is N0 by 2. And this will be N0 by 4. And this will be N0 by 8. And this will be N0 by 16. And in time axis too, we can represent our different T halves. This will be the first T half. This is the second T half. This is the third one. This is the fourth one. So initially at time t is equal to 0, number of atoms will be N0. And at time t is equal to first T half, number of atoms will be N0 by 2. Because after first T half, number of atoms remaining in the sample will be reduced to half. So this will be the number of atoms. And at 2 T half, number of atoms will be N0 by 4. This is the number of atoms. And this will be the number of atoms at 3 T half. And this process repeats. So how we can plot this graph? So as you can see here, the number of atoms decreases exponentially with time. We have earlier studied the relation n is equal to n0 e raised to minus lambda t. That is, the number of atoms in the sample decreases exponentially with time, and the number of atoms will never reaches 0. Number of atoms n will be 0 only if time is infinity. That is, infinite time is required for the sample to disintegrate completely. Now we can derive the expression for T half. So we know from the law of radioactive disintegration, n is equal to n0 e raised to minus lambda t. That is, number of atoms present in the sample is n, and number of atoms present initially is n0. And from the definition of T half, we know at T is equal to T half, number of atoms n will become half. That is, n become n0 by 2. So substituting this condition in the equation, we get n becomes n0 by 2. That is equal to n0 e raised to minus lambda. Instead of t, we have to write t half. Because at t half, n becomes n0 by 2. n0 get cancelled. So we get half is equal to e raised to minus lambda t half. So inverting both sides, we get 2 is equal to e raised to lambda t half. And we are taking logarithm on both sides. That is, log to the base e. Log to the base e is also ln 2 is equal to e gets cancelled. That is lambda t half. And the value of ln 2 or log to the base e2 is 0.6931. It is equal to lambda t half. Or therefore t half is equal to 0.693 by lambda. This is the equation for half-life period. So the final expression for half-life period T half is 0.693 by lambda. So T half is inversely proportional to 1 by lambda. What is lambda? Lambda is the decay constant or disintegration constant of the sample. So half-life period of a sample depends on lambda. If lambda is high, that is, decay constant of the sample is high, what will be T half? T half will be low. That is, a radioactive element with high decay constant disintegrates in a short time. And if lambda is less, T half will be large. That is, radioactive element with less radioactive decay constant disintegrates taking a large time. So the expression for half-life period is 0.693 by lambda, and it depends only on the decay constant, which is a characteristics of the particular material.